Okay. So we have derived a Fourier integral to represent functions defined on the whole real line. Okay, and so now in this section we will apply the Fourier cosine and the sine integrals to represent function defined on the positive real axis, that is starting from 0 to infinity. Okay, all right. All right, so we will discuss Fourier sine cosine transforms in this section. All right, so let's F, all right, be an absolutely integrable complex over real valued function on the positive half axis starting from 0 to infinity. And this function is piecewise continuous. All right, on any finite subinterval of this infinite interval, and has a left hand derivative and a right hand derivative at every point in this infinite interval from 0 to infinity. Right, so this is our assumption. Okay. Now we may regard f of x as the right branch of an even function defined here. Fe of x is defined to be f of x when x is greater than or equal to 0, and f minus x when x is less than or equal to 0. Okay. And this even function defined on the whole real line from mass infinity to infinity. All right, so that by the Fourier integral theorem, that f even x minus plus f even function x plus divided by 2 is equal to 0 to infinity a omega cosine omega x and d omega for all x in the whole real line. Okay, so this is from the Fourier integral theorem. And we know that A of omega x2 divided by pi from 0 to infinity f(e)x cosine omega x and dx. Okay. All right, and by definition, the right branch of the even function from 0 to infinity is exactly equal to the original function f of x itself. Okay, for all omega greater than or equal to 0. Okay, so we have that one. And since fe x minus plus fe x plus divided by 2 is equal to f of x minus plus f of x plus divided by 2 for all x greater than 0. Okay, and f of e minus, so the left hand limit of f of e at x equals 0 is equal to the right hand limit. Okay, so, and we know this is equal to the right hand limit of f, the original function f at x equals 0. Okay, because of that f of f sub e is an even function. So we have that this is the integral. All right, this integral cosine omega x and dx, d omega, sorry, is equal to f of x minus plus f of x plus divided by 2 for x greater than 0, and f of 0 plus for x equal to 0. Okay. Okay. All right. So this is so you can see. So this result follows from Fourier integral theorem. Okay, we developed in last section. All right, so now we give definition. The Fourier cosine transform, okay, of a complex over real valued function f on 0 to infinity is defined to be this function we call f head sub c omega. So this is defined to be the square root of 2 divided by pi from 0 to infinity f of x and the cosine omega x dx for all omega greater than or equal to 0. So the Fourier if exists. Okay, so if exists here. Of course, that we know if f of x is absolutely integrable over this infinite interval, then this function, this f hat sub c function always exists for every omega greater than or equal to 0. Okay, because the magnitude of the integrand is less than or equal to the magnitude of f of x. Okay, all right. So that but if f of x is not absolutely integrable, then the Fourier cosine transform may exist or may not exist. Okay. So we also denote the Fourier transform, the Fourier cosine transform fc hat of f as fc f if exists. Also, note that with all this notation, we see that the Fourier cosine transform of f, okay, is equal to the function is equal to f hat c, and which is just the square root of pi see here times a times a function. Okay, this a function here. Okay. And you will see the reason why we use the a scaled a function because of the symmetry, as we will see later. Okay, so this is the Fourier transform we have. Now we state the following theorem, right, which says the existence of inverse Fourier cosine transform. All right, so let f be an absolutely integrable complex over real valued function defined on the positive real axis. Okay, and we know that f hat c it's Fourier cosine transform. Okay. Now, if f is piecewise continuous, okay, on any finite subinterval of the positive real axis and has left hand derivative and right hand derivative at every point in 0 to infinity, then fx can be back by this formula from 0 to infinity, f tilde c omega cosine omega x and d omega for all x greater than or equal to 0. Okay, so this is true for all x in 0 to infinity, except at points x is 0 where f is discontinuous. Okay, and there the value, okay, of the integral, okay, equals f of x minus plus f of x plus divided by 2 if x is 0. If x is 0 greater than 0, or equal to f0 plus if x is 0 equal to 0. Okay. So this is called existence of inverse. Yeah. Okay. So this is basically, right, so the proof, all right, the proof is, this follows from the Fourier integral theorem. Okay. Okay, now the integral, right, in the right hand side of, right, say here, we say this equation would be 11.8.1, okay? So in the reference side of equation 11.8.1 is called the inverse Fourier cosine transform of f c all right, and denoted as f cos fc cosine minus fc, which is a function, okay, on 0 to infinity. So we have the pair that f of x, okay. So any f of x, they go to f of c hair omega by the Fourier cosine transform, and then goes to the inverse Fourier cosine transform to a function, okay, and this function is actually equal to a function, okay, and this function is equal to the original function f of x at every x which f is continuous. So if we call this, go back to say say f tilde. Maybe I use I use f of x, and this one is equal to f of x if f is continuous at x, okay, and is equal to so basically I have to say that is equal to f of minus plus f of x plus minus divided by 2 if x greater than 0, and f of 0 plus if x equals to 0. Okay. So the inverse Fourier cosine transform back to this one, but with some condition. Okay. So so if here that here we assume this one is piecewise continuous. Condition 1 on each finite interval, subinterval for each finite on each finite subinterval of 0 infinity. Okay, and second, has left hand derivative and right hand derivative at every point, okay, in 0 to infinity. So if the starting function satisfies these two conditions, then of course this function must be absolutely integrable. So it has the Fourier transform. Okay, so this is the Fourier cosine transform. Right? So it's a function, okay, on the positive real axis. And now we can do the inverse Fourier cosine transform and render with a function. Okay, and this function is actually closely related to the original function. All right, so you can see here. So as you can see now, if the original function f is continuous, okay, at a point x, then then this f tilde hey, f of x is equal to f of x. Okay, so we have this pipeline here. We have this pipeline. All right, and on the other hand, so the previous discussion is based on that we regard the original function as the right branch of an even function defined on the whole real line. Okay, even though the original function just defined on the positive real axis. Okay. So now, this time, on the other hand, okay, we may regard f of x, okay, as the right-hand branch, okay, of an odd function. So this definition is defined to be f of x if x greater than 0, and 0 if x equals 0, and the minus f minus x if x is less than 0. Okay, and this odd function is defined on the whole real line from minus infinity to infinity, so that we know x minus plus f odd x plus divided by 2 is equal to b, the integral of b omega sine omega x and d omega for all x in minus infinity to infinity. All right, so this is from the Fourier integral theorem. And here, the b omega is equal to 2 over pi from 0 to infinity, f odd function, and the sine omega x and dx. Okay, and as we know that if x greater than 0, that the f odd function is equal to f of x. So this is equal to from 0 to infinity f of x sine omega x and dx. Okay, for all omega greater than or equal to 0. Okay, so this is from the, again, from the Fourier integral theorem. Okay, so now if we look at x greater than 0, so for x greater than 0, we know the fr function is equal to the f function. So this is equal to 2 for all x greater than 0. Okay, and we have here the integral itself. Okay, omega, and the sine d omega, which equal to f minus f of x plus divided by 2 if x greater than 0, and it's equal to 0 if x equal to 0. Why? Because if x is 0, so this is 0, right? Sine 0 is 0, and so the integrand is 0, so the integral is 0. Okay. So of course, we always go back to the 0 here. All right, so now we give a definition. Another definition, the Fourier sine transform. So the Fourier sine transform of a complex or real valued function f on the positive real axis is defined to be here fa s omega is defined to be square root of 2 pi and f of x and the sine omega x d of x for all omega greater than 0 if exists. And of course, if the f function is absolutely integrable, if it's absolutely integrable over this infinite interval, then this function always exists, right? The integral exists, so the function exists and defined on the positive real axis. Right. And now we also denote, all right, the Fourier sine transform f of f as fs sub x of f if it exists. Okay, and we know that x equal to fxa, and which is actually equal to square root of pi divided by 2 times b. Okay. All right, so we have step 1. Okay. All right, and then we have a corresponding existence theorem of inverse Fourier sine transform. Right, so we let f be an absolutely integrable complex over real valued function defined on 0 to infinity, and FSA, it's Fourier sine transform. Okay. Now, if f x piecewise continuous on any finite subinterval of 0 to infinity, this interval, and has left-hand derivative and a right-hand derivative. At every point in 0 to infinity, then fx is equal to the same. So has the same, you can see the same scalar, square root of 2 over pi, infinity to 0, f omega, and sine omega x and d omega. Okay, for all x in 0 to infinity, all right, except at the points, okay, except at point x0 sub 0, where okay, sorry, this must be an open interval, okay? So x must be greater than 0. This is not closed, must be open. Okay? At points where f is discontinuous. Okay? There, the value of the integral equals the average of the right-hand limiter and left-hand limiter. Okay, and if f of 0 equal to 0, then the value of the integral at the x equals 0, which is 0, equals f0 again. Okay, because the value of the integral at x0, which is 0, right? Then equals f of 0. Okay, so so you can see that this actually is from here. Okay, from this formula. So this now the right hand side of this equation, will be denoted as So now the integral in the right hand side of 11.8.2 is called inverse Fourier sine transform. It's called inverse Fourier sine transform. Of FAS. Okay, and denoted as inverse FA, which is a function on 0 to infinity. Okay, so it's a function. Okay, so again, we have f of x, and we can do the Fourier sine transform to get this function, and then we do the inverse Fourier sine transform, and we get a function of x here. And this function of x is actually equal to derivative if x is greater than 0, and this is equal to 0 if x equals to 0. Okay, so we have that. So you can compare this one with this path here. Okay, you can go there. So maybe we don't use UF. So we will use that. Prong. No, prong is not good. Maybe you use double tilt. Okay. So you see that they are, if x greater than 0, they are the same. You can see here, they are the same here. But for x equals 0, if we do the inverse Fourier sine transform, the value is 0. But if we do the inverse Fourier cosine transform, the value is the right-hand limit of fx at x equals 0. So this value may not be the same. Okay, you can see them. Okay, and again, we know that this function must satisfy two conditions. So it is piecewise continuous on any finite subinterval of 0 to infinity. And the second has a left-hand derivative and a right-hand derivative at every point in 0 to infinity. Okay. So for that, okay, and we should know that that this one, the Fourier cosine transform, as we know, this is this one. Okay. Pi over 2. Oh. 2 over pi, sorry. Maybe I write, there's no space here. Okay, and this one, again, so you can see the symmetry of these two transformation, okay, the symmetry. And for here, we know this. Okay, and this one. Okay, so you see that they also, you can see these two integral are the same, except that here, this is f of x, this is f hat sub x of omega. Okay, so that. Okay. Now, because the integration is a linear operator, okay, so we know the Fourier sine transform as well as the Fourier cosine transform, they are also linear. So we can state the linearity. Okay, of Fourier cosine and sine transforms. Right. So if f, g are absolutely integrable, complex or real valued function, on the positive real axis, and AB are constant. All right. Then of course AF plus BG is absolutely integrable. Okay, on 0 to infinity, and we have the Fourier cosine transform of this linear combination is equal to the same linear combination of the Fourier cosine transforms. Okay. And similarly, for the sine transform, Fourier cosine transform, we have okay. And the proof is trivial. Okay, by observing that okay, the absolute value of this linear combination is then equal to A and f of x plus b g of x. Okay, so we have some typos in my notes. Okay. So, from this, we can show that this linear combination of function f and g is absolutely integrable. Okay, because f and g are absolutely integrable. Okay. All right. And now we will give a theorem. So the following theorem is useful when solving partial differential equations. Okay, we will soon discuss. So very well. Theorem 11.8.1 is about Fourier cosine and the sine transform of derivative. All right, and so let f be differentiable okay, a differentiable complex over real valued function. Real to infinity, and f prime, and that its derivative is piecewise continuous on any finite subinterval. Okay, so any finite subinterval of 0 to infinity. Okay. Now we assume that f of x goes to 0 as x goes to infinity. And the Fourier cosine transform of f, Fourier sine transform of f exists. Okay? So we assume and of course that this is guaranteed. If f is absolutely integrable. Okay, on 0 to infinity. Okay, so both of them. So the existence of these two transforms is guaranteed. All right, if f is absolutely integrable, but we make it more general. So we just assume, all right, several things. First, f is differentiable. Okay, and its derivative is piecewise continuous, okay, on any finite subinterval. And second, we assume that f of x approach to 0 as x goes to infinity, and the Fourier cosine transform and the Fourier sine transform of f exists. Then the Fourier cosine transform of its derivative and the Fourier sine transform of its derivative exists, and has the relationship that the Fourier cosine transform of the derivative of f is equal to the omega times the sine transform of f minus this constant f0. And the Fourier sine transform of f1 is equal to omega times the Fourier, is equal to minus omega times the Fourier cosine transform of f. Okay. So we have a pair of relation. Okay. Okay. So we can. So with these two formula, we can obtain the Fourier cosine transform of the derivative of f. Okay, and the Fourier sine transform of the derivative of f. Okay, in terms of the Fourier sine transform of f and the Fourier cosine transform of f. Okay. Okay, now we give a proof of this theorem. Okay, now for any L greater than 0, we have so okay. So let's see here. We give like fix an L greater than 0. Okay, right. So now, since f prime of x is piecewise, is piecewise continuous on 0L. Okay, so they are points. All right, so they are points that this is depends 0, x1, x2. Okay, so yeah, they are points such that f prime of x is continuous. Okay, it's continuous at on xi plus 1 minus 1 xi for all okay, for all open interval. Okay, and we know that f prime x0 plus f prime x1 minus f prime x1 plus f prime xn minus f prime xn plus okay, plus minus okay, and f xn plus 1 and minus. Okay, all these limits exist. Okay, right. So this is the meaning of piecewise continuous. Okay, so we know about those things together. Okay, and so now if we do the integration cosine omega x dx, so this is equal to summation I from 1 to n plus 1, and you can have x I minus 1 xi. Okay, and so I think we just up to n, right? So I think n will be sufficient. plus minus plus, oh, okay, minus plus minus plus minus, okay, exists. Okay. Now, so this is from I from 1 to n. So the integration, so we can cosine. Okay. Okay, and so you see that that f prime of x is continuous in this interval. Okay, in each subinterval. Okay, so by the integration by parts, we know. Okay, so that the cosine omega x, and this is f prime of x dx. So we have f of x here, and now we have minus omega sine omega x and dx. Okay. All right. So this integral. We have cosine, so we have f of x and cosine omega x. Okay, and this is from xi minus 1. Okay. All right, and minus this integral. So we have minus of xi minus 1 xi, okay, and omega f of x sine omega x, oh, minus omega, okay, and dx here. Okay, so you have this one. Okay, and so we go to here by integration by parts. Okay, so we have that by integration by parts. Okay, and so that the integral so we have, and so we do the substitution here. The f of xi and cosine omega xi minus f of xi minus 1 cosine omega xi minus 1. Okay. Plus summation I from 1 to n xi minus 1 to xi, and this is omega So omega is here, and the f of x sine dx. Okay, so that's the second part. Yeah, together. Okay, and we can cancel them. So this is come to f of xn cosine omega xn minus f of x0 cosine omega x0 for here, and plus, and this is from 0 to L, and the f of x sine omega xn dx. Okay, but we know x0 is 0, and xn is equal to minus 1, sorry, and xn equal to L here. Okay, so we have the f of L, okay, cosine omega L minus f0, and cosine 0 is 1. So it's this one, and plus omega. Okay, all right. So we have that, and similarly, we can do the f prime of x sine omega x dx becomes to be f of L and the sine omega L. But because sine 0 is 0, so we don't have this term, minus omega f of x cosine omega x and dx. Okay. So now we have minus sign. This is because that if the kernel involve the sine, then sine omega x give us the omega times cosine omega. We don't have the minus sign here. Okay. Okay, so we have this one. Now, since FCF and FXF, so the Fourier cosine transform and sine transform exists, and we know that goes to 0 as L goes to infinity. So we have, okay, we can have that this integral f prime of x cosine omega x dx. This is actually equal to the limit as L goes to infinity. So this is an improper integral. Okay. So this is f prime of x cosine omega x dx. Okay, and what is this? So we can put this into there. So this goes to the limit L goes to infinity FL and cosine omega L. Okay. And the minus F0 plus omega and limit L goes to infinity to L sine omega x dx. Okay, we have that. And that the cosine function is bounded by 1, but the f of L goes to 0. So this term goes to 0 as L goes to infinity. And as L goes to infinity, this becomes the improper integral. Okay, so that this is equal to square root 2 pi. Okay, so now we move this here, omega, and 0 to infinity, f of x. Maybe I write right here. Omega times pi, infinity f of x, minus f0. Okay, and this is equal to omega, the Fourier sine transform of f. Okay, of omega minus all right. So this exists, and as we know that this is equal to. So this is our Fourier cosine transform of the derivative of f. Okay, so we have that. So we have shown that the Fourier cosine transform of the derivative of f, okay, is equal to omega times the Fourier sine transform of f minus this constant, okay, minus this constant. Right, so this is, and when we look at the Fourier sine transform of the derivative of f, and we see that. Okay, which is okay, and this one. So this is an improper integral, and so this is equal to okay. So now we will use this equation here. So this becomes 2, then limit L goes to infinity FL and the sine L omega or sine omega L minus limit cosine omega x dx, okay, from here. But as L goes to infinity, this term is 0. So we have only this term. So we have okay, and we have, so the improper integral, this is exactly the Fourier cosine transform of f. Okay, so this is okay. So we prove our theorem. So if so we have this formula. So if the f is differentiable and is in its first derivative is piecewise continuous on any finite subintervals, then we have, and also we assume that the original function goes to 0 as x goes to infinity, and we assume that the Fourier cosine and the Fourier sine transform of f exist. Then this condition guarantee that the Fourier cosine transform and the Fourier sine transform of the first derivative of f exist, and they are related to the Fourier sine transform and Fourier cosine transform of f, okay, by these two formulas. All right. Now, if f is twice differentiable complex or real valued function on 0 to infinity, okay, and its second derivative is piecewise continuous, okay, on any subinterval of 0 to infinity. And assume, and if f of x goes to 0, f prime of x goes to 0, as x goes to infinity, and the Fourier cosine and the Fourier sine transforms of f exist, right? Then, by repeatedly applying the previous theorem, 11.8.1, then the Fourier cosine transform of the first derivative, Fourier sine transform of the first derivative, Fourier cosine transform of the second derivative, Fourier sine transform of the second derivative, all exists. And we have here that the Fourier cosine transform of the second derivative, which is, we know is omega, times the Fourier sine transform of its first derivative, minus square root of 2 pi, and f prime 0 here. Okay, and again, we apply this omega square and Fourier cosine transform of f minus, okay, so we have minus here, square Fourier cosine transform of f, and the minus equal to 2 pi f prime 0 here. Okay, so this is the, we have that. And the Fourier sine transform of the second derivative is minus omega f the cosine. The Fourier cosine transform of the first derivative, and this is minus omega square Fourier sine transform of f, okay, plus omega square root of 2 divided by pi, and f is 0. Okay. So we have that. So this is by, we will repeatedly apply that. Okay, so let me correct the table A there. Okay, all right, so we have this result. And an operation called convolution among between two functions is often occur in science and engineering. So definition. So we define here the convolution we call f star g of two complex or real valued functions f and g on the positive real axis, okay, at the point x in the positive real axis is defined to be this integral. So the convolution of f of g at x is defined to be this integral from 0 to x f of p, g of x minus p, and dp. Okay, and this is also equal to f of x minus p and g of x dp. Okay, if it exists. Right? Okay, so these two integral will be the same just by change of variable. Okay, you can see that. Okay, so this is the right. So this is a convolution of two functions defined on the positive real axis. You see, starting from 0 to infinity, and so that for each point x in this positive axis, we define the value of this convolution at this x is equal to this integral, if it exists. So if this exists for every x in this interval, then of course the convolution defines a function, a new function, okay, on the positive real axis. Now we will give sufficient conditions for the convolution function to exist. Okay. So if the theorem 11.8.d, so this one gives a sufficient condition for the convolution to exist. So if f, g are absolutely integrable functions on 0 to infinity, then the convolution then the convolution f star g at x of f and g exists for almost all x in your infinity. Okay, so the f and g are absolutely integrable function implies that the convolution exists for every x, for almost all x, which means that the convolution may not be exist at some point, okay? But we collect the length of all points where convolution does not exist, then the length is equal to 0, okay? So this is the reason why we call almost all, okay? Right, so convolution defined, defined for almost all x in here, and we can redefine the convolution. The value of the convolution is 0 when the convolution does not exist. Okay. So anyway, and furthermore, so that the convolution so if fg are absolutely integrable, then the convolution is also absolutely integrable over 0 to infinity. And if we integrate, all right, if we integrate this interval, okay, this integral, the absolute value of the convolution, okay, if we do it, then this integral will be less than equal to the product of these two integrals. Okay. So the proof. So a reference is given in the lecture notes. Okay. Okay, so what do we need to know is that when f and g are absolutely integrable functions, then we do have a convolution function. Okay, the convolution of f and g, which is defined for every x, almost all x in this positive real line or real axis. Okay, and the convolution function is absolutely integrable too, because that this integral is upper bounded by the product of these two integrals. Okay. Okay, and so that we will have an interesting, we call the convolution theorem. For Fourier cosine and sine transform. Right? So if f and g are absolutely integrable, complex our real valued function on 0 to infinity, then from the previous theorem we know the convolution over MG exists for almost all the x in this positive real axis, and this convolution is absolutely integrable. Okay, so it has, so that in this case, so that this convolution has Fourier cosine transform as well as Fourier sine transform, and so the Fourier cosine transform, so the Fourier cosine transform of the convolution is equal to, okay, the scalar times the Fourier cosine transform of f times Fourier cosine transform of g minus Fourier sine transform of f times Fourier sine transform of g. Okay, this one. Okay, and the Fourier sine transform of the convolution is equal to square root of pi over 2 the Fourier sine transform of f, the Fourier cosine transform of g. Oh, maybe I use this. The Fourier cosine transform f and Fourier sine transform plus the Fourier the Fourier sine transform of f, the Fourier cosine transform of g. Okay, yeah. Very interesting. Okay, we have this result, and this theorem will be proved the next section. Okay, when we talk about the Fourier transform. Okay, so anyway, so we have the theorem. This is quite useful. Okay, it's called the convolution theorem for Fourier cosine and sine transforms. Okay. Okay. All right, so we will go to the last section of chapter 11, talk about the Fourier transform. Okay, so that in the previous section, we used Fourier cosine transform and the Fourier sine transform to transform a function defined on the positive real axis. Now we will deal with a transform on the function defined on the whole real line. Okay. All right, so we let f be an absolutely integrable complex or real value function defined on the whole real line from minus infinity to infinity, and which is piecewise continuous on any finite subinterval okay, on any finite subinterval of minus infinity to infinity, and has a left-hand derivative and a right-hand derivative at every point in the whole real line. So by the Fourier integral theorem, right? So we have that the f of x minus plus f of x minus plus divided by 2 is equal to the integral with the integrand, which is a omega cosine omega x plus b omega times sine omega x, right? And d omega for all x in the whole real line. And where the a omega is 1 over pi of the integral from minus infinity to infinity f of x cosine omega x dx, okay, and the b omega is 1 over pi from minus infinity to infinity f of x sine omega x dx for all omega greater than or equal to 0. Okay, so this is from the Fourier integral theorem. Okay. Okay, now this time we will do the substitution. So we substitute the a omega by this integral, all right, and substitute the b omega by this integral. So by substituting a omega and so maybe we say that this is 11.9.1, this is 11.2. So by substitution 11.9.2 back to 11.9.1. Now we have the following result. that f x minus plus f of x plus divided by 2 pi 0 to infinity. Now, and the f of u and of cosine omega u cosine omega x. So maybe we will use in here, instead of x, we use u. Okay, to prevent confusion. So we just do the substitution back here. Okay, here. And so we have cosine omega u and cosine omega x. Okay. So we have cosine omega x and plus sine omega u, sine omega x here. All right, and du first. Okay. So we say that. So we have du first and the d omega. Okay? D omega there. All right. And so we have an iterative integral f of u here, and the cosine omega, and this is and the x minus u, okay, and the du and the d omega. Okay. Right. So this is by the cosine some function, some identity. Okay. See here. Now, if we look at, so you see here, we have this integral. And this integral, as you can see, this integral, okay, it's a function of omega, because as you see that, you integrate over u, and so that this is a function. So this is, okay. So it's a function of omega, okay? All right, so we fix, here we fix an x in the real line. Okay, so fix an x here. And so this is a function of omega here, a function of omega. All right, so we call it, for example, we call it, say, f omega. Okay, we call it f omega. And we look at, so this omega, can be defined for every voice which can be defined on the whole real line. Okay, and we see that f minus omega, if we do nullate, so this is f of u, and cosine minus omega, and x minus u, and du here. Now, because cosine is an even function, so this becomes to f of u, and cosine omega, x minus u again, du. And so this is f of omega. All right, so f minus omega is equal to f omega. So f is an even function, okay? And so that we can do the things that we can extend the interval from minus infinity to infinity, okay, of the f of omega and d omega, right? So it's see that? Okay, so we know this is 0 to infinity, f omega d omega. Okay, but this is equal to 1 over 2 pi of so yeah, so it's an even function, so we can write it down 2 pi minus infinity to infinity. Okay. Okay, and so we have 1 over 2 pi f of u cosine omega x minus u du and d omega. Okay. Okay, so that the first one is here. Also, now, if we define g of omega to be sine omega x minus u du, okay. Okay, so if we define this one, okay, and so which is a function defined on the whole real line, okay, for all w, right? And we look at g minus omega. Okay, and because sine is an odd function, so we have minus so this is minus g of omega. Okay, so that g of omega is an odd function. Okay, so this implies that the integral of g of omega, right, it's 0, okay, because it's an odd function. Okay, so this integral is 0, i.e. So we have sine omega x minus u du and d omega. It's 0. Okay. All right, so we combine this, this is 0, right? So we combine this integral, right, together. So we find that thus we have f of x minus plus f of x plus divided by 2, which is equal to 1 over 2 pi. Okay. And f of u cosine omega x minus u du and d omega plus I 1 over 2 pi and f of u sine omega x minus u du and d omega. Okay. So this term is 0. All right, this term is 0. Okay. All right, and so by the linearity of integration, so now we have here cosine omega x minus u plus I sine omega x minus u here and du and d omega. Okay. All right. Now by the Euler's formula, we know this one is exponential of I omega x minus u. Okay, by Euler's formula. Okay, so this one, and so that's so finally we have a 2 is equal to 1 over 2 pi f of u exponential function I omega x minus u and du first and dw. Right, and we will split 2 over pi by their square root, and okay, and this one we have u and the du, right? So we have two terms. This exponential, this is exponential function, so this is equal to ei omega x times e minus I omega u. Okay. All right, so we retain the e minus I omega u here. Okay. Oh. F of u e minus I omega u and the du here. So this is our inner integral. And the phasor I omega x and the d omega here. Right? And this is true for all x in the whole real line. Okay. And so this representation, which is called the complex Fourier integral. Right? So originally we have the the Fourier integral only, right? Where is the Fourier integral? Here. So originally we have the Fourier integral here. Okay, we have Fourier integral, and we turn the Fourier integral. So this is the Fourier integral representation we have, right? This is our Fourier integral. Right? So this is our Fourier integral representation of f of x. And we turn the Fourier integral representation into complex Fourier integral representation. Okay, complex Fourier integral representation. All right, so this renders a definition. The Fourier transform of a complex, our real valued function f on the whole real line is defined to be here f hat omega is defined to be 1 over 2 pi. So it's inside the integral f of x e minus I omega x dx for all omega in the whole real line. If this function exists. Okay. Of course, if f of x is absolutely integrable, then its Fourier transform always exists. Okay, and omega for all the omega in the whole real line here. Okay, so this is the Fourier transform. Okay, and so we will denote the Fourier transform so that so this one will be denoted as f of f. Okay. As before. Okay, so now the following theorem states the existence of Fourier transform. Okay, so if f is absolutely integrable, complex, or real valued function, on the whole real line, then its Fourier transform f hat, which is f of f, exists. Okay. Furthermore, f hat is uniformly continuous, okay, on the whole real line. Okay. And the Fourier transform goes to 0 if omega goes plus or minus infinity. Okay. Okay. And this fact is from the Riemann-Lebesgue lemma. Right? And a proof is given, so please see the lecture note. All right. So I have given a detailed proof for you in the lecture note. So actually, this is the. So I can say that this is due to Riemann-Lebesgue lemma. Okay, this is due to the Riemann-Lebesgue lemma, and of course that so the Fourier transform is very nice, because the original function f just maybe piecewise continuous only. Okay, all right, but the Fourier transform must be continuous, and furthermore is uniformly continuous. So this is much well behaved. But so even though f hat is uniformly continuous on the whole real line, and we know that its value goes to 0 as the omega, the angular frequency, goes to infinity, positive or negative infinity. But in general, the Fourier transform may not be absolutely integrable, all right, over the whole real line, may not. Okay, but the Fourier system. So if this is the case, then we may not do the reverse, to go back to the x function. Okay. But the following theorem gives us the possibility. This is called the existence of inverse Fourier transform. Okay, so let f be an absolutely integrable function on mass into infinity, and so its Fourier transform exists. So f hat is Fourier transform. Okay. Now, if furthermore f is piecewise continuous, on any finite subinterval of the whole real line, and has a left hand derivative and right hand derivative at every point in the whole real line. Okay. All right. Then f of x will equal to 2 pi okay, so the exponent part of this space is I omega x instead of at here minus I omega x. Okay. So this one, okay. So this is for all x in the whole real line except at the points x is 0 where f is discontinuous. Okay. There, the value, so there means that the point where f is discontinuous, where the value of the integral of the complex Fourier integral equals this average. Okay, this average. Okay, and now, so let's say this is the 11.9.3. This is the 11.9.4. Okay. Now the integral in the right-hand side of the equation 11.9.4 is called the inverse Fourier transform of Fa, denoted as F inverse of Fa. Okay, so F inverse of Fa, okay, it's a function of x. It's actually square root of 2 pi so that the inverse Fourier transform of f hat is a function defined for all real line. Okay, all real line there. So we have the path that f of x will go by Fourier transform to FA over omega, and go by inverse Fourier transform to we said F tilde. Okay. And this F tilde is actually equal to f of x minus plus f of divided by 2. Okay. Okay, for all x in R. Okay. So the path is that fx go to there, but to have this result, now it is required that the function is piecewise continuous. On any finite subinterval of the whole real line, and the second has left-hand derivative and a right-hand derivative at every point in R. Okay, here. Okay, and then we notice that the Fourier transform here, this is 1 over 2 pi, square root of 2 pi, and f of x exponential minus I omega x and dx. And this one is 1 over 2 pi from minus infinity to infinity f hat omega and exponential I omega x and d omega. Okay. All right. So they are very symmetric, except that the kernel, the weighting function, are different. Here is e to the minus I omega x, but here we have e to the I omega x. Okay, so they are different. You have that. Okay, so this is the Fourier transform. This is the inverse Fourier transform. And the path goes, you can see that basically we can recover the original function f of x by using the inverse Fourier transform. Okay, if the f of x satisfies these two properties, okay, and you can see that f tilde x is equal to f of x if f is continuous at x. Okay. So we have such a result. Okay. So, in the theorem here, 11.9.8, we know we can go back to our function f of x. If there are some conditions here, we put two conditions for x to have and to guarantee that we can go back, okay, by using the inverse Fourier transform. And another theorem, okay, again, for the existence of inverse Fourier transform, it's like this here. So this is another version. So if f and its Fourier transform okay, fa are absolutely integrable over the whole real line, then, okay, so if f is absolutely integrable, then f hey, the Fourier transform always exists. And furthermore, if the Fourier transform f hey is also absolutely integrable, then of course the inverse Fourier transform, right, exists. And we have that the inverse Fourier transform of f hey is equal to the original function for almost all x in R. Okay, so this is guaranteed, just like here. That's like here, because that if we have a countable discontinuity, all right, countable discontinuity for the f of x over the whole real line, then you can see that f and f tilde are equal for almost all x in R. And so this is the same situation, that they are equal for almost all x in R. Okay, so they are equal. And if, in addition, okay, f is continuous, so if in addition f is continuous on the whole real line, then the equality, okay, for this inverse, the inverse Fourier transform of f hat will be equal to for all x in R, right? So everyone, okay. So if f is continuous, okay, and the proof is rather involved. So a reference is given in the lecture notes. Okay, but this theorem is quite useful in practice. Yeah, in practice that you will know. So you just check that f is absolutely continuous, absolutely integrable, and then you check whether its Fourier transform is also absolutely integrable. If the answers are both yes, then that we have this identity for almost all x in R. And furthermore, if we know f is continuous on the whole real line, then the equality is exact for every point in R. Okay, so this is a very nice result. And again, we have linearity of the Fourier transform. Okay, so if f and g are absolutely integrable, okay, over, so are absolutely integrable functions on the whole real line, and AB are constants. Okay, then AF plus BG is also absolutely integrable over the whole real line, and we know that the Fourier transform of AF plus BG is equal to A times the Fourier transform of F plus B times Fourier transform of G. Okay, now the Fourier transform. So if a function f is differentiable, okay, so we may ask for the Fourier transform of the first derivative, okay, and want to know the relationship of the Fourier transform of its first derivative to the Fourier transform of f itself. Okay, so here is the theorem, 11.3.3. It's called the Fourier transform of derivative. Okay, so now we let f be a differentiable function. Okay, so it's a differentiable complex or real value function. Defined on the real line. And its first derivative, piecewise continuous. Okay. On any finite subinterval, okay, any finite subinterval of the whole real line. Also assume that f of x goes to 0 as x goes to plus or minus infinity. Okay, and the Fourier transform of f exists. Okay, we assume that. Then the Fourier transform of f prime exists, and we have f. The Fourier transform of f prime is equal to I omega, the Fourier transform of f. Okay. So this is a nice formula. A nice formula to have here. So the proof. All right, so since f prime is piecewise continuous, okay, minus L to L, greater than 0. Okay, so we have here the integral f prime of x e minus I omega x dx is equal to f of L e minus I omega L minus I omega L minus f of minus L e I minus L plus I omega minus L f of x. Okay, by integration by parts. as we did in the proof of theorem 11.8. When we do that for point 1. Yep. Okay. So this is from the integration by parts. As you see, that E for I, omega x, f prime of x, dx here. So this is x. And we have, when we do the minus I omega, E dx, right? All right, so we have this one, okay, by integrating by parts. So we have this integral. Now we let L goes to infinity, okay? So this is goes to the Fourier transform of f prime. Now, so as L goes to infinity, we know that the Fourier transform of f prime of omega, which is 1 over square root of 2 pi. So this is 1 over square root of 2 pi. We have all right, and so we have the limit infinity of FL. Okay, minus F minus L, this part, plus I omega. F of x, E I omega x dx. But now, so as L goes to infinity, this goes to 0, but this is always bounded by 1. This bounded by 1, this goes to 0, so this limit goes to 0. And the limit goes to the improper integral, so this is I omega. And this is I omega, Fourier transform of f. Okay. Okay. All right. So we have this result. And so you can apply the theorem twice, right? When we know that fx is twice differentiable, okay? And so if fx twice differentiable and the second derivative is differentiable on the whole real line, and the second derivative x piecewise continuous okay on every sub-interval of R, and if f of x goes to 0 and f prime of x goes to 0 as x goes to plus minus infinity, and the f of f exists, then we have that the Fourier transform of the second derivative, which is equal to I omega of the Fourier transform of the first derivative, is equal to minus omega square, the Fourier transform of f. Okay, so we have this nice formula. Now we define the convolution of two functions defined on the whole real line. The convolution f star g of two functions f g on the whole real line, it's a point x in R is defined to be, so f star g of x defined to be the integral f of p gx minus p and dp. And this is equal to f of x minus p gp dp by change of variable, okay, if exists. Okay, and we have a companion theorem to describe the existence of convolution. Now, so again, if f, g are absolutely integrable functions on the whole real line, then the convolution f star g of x of f and g exists for almost all x in R. Furthermore, the convolution f star g is absolutely integrable over R. And And then when we do the integral, this integral is upper bounded by the product of the two integral. And the statement not finished yet, so we need. If, in addition, either F or G is bounded on R, then the convolution F star G of X of F and G, okay, exist for all X in R. And this condition is bounded on R. Okay, so this is very nice because absolute integrability of both F and G only guarantee that their convolution exists for almost all point X in the R. Okay, in the R. But if either one is bounded on R, then the convolution exists for every X in R. Okay, yeah. Not just almost all. And the convolution, this function, is a function on R, and it's bounded. So it's bounded. So this is very nice. And if, in addition, the bounded function, so the bounded function F or G is continuous on R. Okay, then the convolution is also continuous on R. Very nice, okay? So, proof references are given in the lecture notes. Okay. All right, so this is a nice theorem to know the existence of convolution, and it gives further properties of the convolution when we put more conditions on F or G. Okay. So in particular in here, if either F or G is bounded, right, then and F and G are absolutely integrable, then their convolution exists for every point in the real line. And if the bounded function is continuous, then this bounded function is also continuous. Okay. All right, and so now, so we have the convolution theorem for the Fourier transform. Fourier transform. Okay. Now, so if f, g are absolutely integrable, okay, functions on the Fourier line, then from the because f and g are absolutely integrable, all right, and so that their convolution exists for almost all x, right, and and this convolution is absolutely integrable, so we can take the Fourier transform of the convolution of f and g. Okay. So the Fourier transform of f and g here, and this one is equal to the square root of 2 pi times the Fourier transform of f times the Fourier transform of g. Okay. Right. So basically, the Fourier transform of the convolution of f and g, okay, is equal to the product of the Fourier transform of x, f, and the Fourier transform of g, and scaled by the square root of 2 pi. Okay. So this is also a very nice properties. Okay, and again, for proof, please see the lecture notes. Okay, so I give this a proof for this convolution theorem. For this convolution theorem here. Okay, so now I make a remark here. The first one, if the product of the Fourier transform of f and g, so this is the product, okay, is absolutely integrable, okay, over R, then we have we take the, okay, so if we take the Fourier integral of this product scaled by 2 pi, and this one okay, so this is equal to, this one is equal to this, okay, all right. And okay, so first of all, we have this one, okay, and this exists for all x in R. Okay, this exists for all x in R. Okay, and this x function is equal to the convolution, the original function, right, for almost all x in R. So we can go back to the convolution of f and g. Okay, and this is from our theorem 11.9.b. 11.9.b there. Okay. right? So if the Fourier transform is absolutely integrable, then we can do the inverse Fourier transform. And this inverse Fourier transform will equal to the original function f of x for almost all x in R. Okay. And then it states that if f is continuous, then this is equal for all x. So now if in addition, at least one of f or g is continuous and bounded, then on R, then the convolution f star g of f and g, okay, is continuous on R, and so that f star g of x comes to f hat omega g hat omega ei omega x dx for all x in R. So the equality is exact for every x in R. Okay, and this is by theorem 11.9.c. Okay, so we have that. So this the convolution here. Okay, the statement C says that. Okay, you know. So if one of the FRG is bounded and continuous, then we know that the convolution exists for every point on R, in R, and is also continuous on R. Okay, and so we have exactly the same thing here. Okay, so this is quite nice. And the second remark is that we mentioned a theorem in 11.8. Okay, this theorem can be deduced from the convolution theorem 11.9.4. This is as an exercise. Okay. All right. So now, okay. So I finish section 11.9. Okay, and so I stop here, and we will start with the topic of partial differential equation next week.